to part 3 of the series of lectures on special relativity. Today, we'll be discussing relativistic effects and paradoxes. If you haven't watched parts 1 and 2, the links are in the description below. So today we're going to be summarizing a bit of what we did last time. We're going to discuss some relativistic effects, one of which is shown in the lovely diagram on the right. We'll also be discussing a bunch of paradoxes, but focusing in specifically on one. And this is going to be our last lecture in the special relativity section. So we'll be thinking about some more general things that we can do with it, look back at everything that we've done so far, and also look forward to next time. So let's take a look at what we explored in part 2. We discovered space-time diagrams, which, as you can see on the right, are essentially just graphs of x versus time, or x versus the speed of light times time. Of course, sometimes we set the speed of light c equaling to 1, as we did on occasion in the previous lecture. So that essentially results in this lovely graph here with some lines going from the top left down to the bottom right and top right to the bottom left, which are represented by the cosmic speed limit, essentially, of speed equaling c or negative c, if we're counting the velocity in the other direction. So we also get these lovely curves known as invariant parabolas. And the invariant parabolas are caused, as we discussed last time, by the invariance of the interval between two different points in our space-time diagram. So that interval is always going to be invariant regardless of the reference frame. We also discussed how to go from the Galilean transformations on the left, which worked with Newtonian mechanics and switching between reference frames, to working with relativistic reference frames and thus going to Lorentz transformations, which will be slightly more complicated, albeit very similar equations on the right-hand side. And the frames that we're switching between are the regular frames represented by x, y, z, and t, and the prime frames represented by the x prime, y prime, z prime, and t prime frames. Additionally, there's this little bit of a constant here known as gamma, the Greek letter, and that is represented by gamma equals 1 divided by the square root of 1 minus v squared over c squared. Something interesting to note about gamma is that as your velocity gets higher and approaches c, this term right here will get greater. This term right here will get greater and greater, but then we're taking 1 minus that. And since this is going to be a decimal, then 1 minus this is going to get very small. The square root of that is also going to be a fairly small number. But since we're taking 1 over the square root, that means that this number actually gets bigger overall. So as we speed up, gamma actually increases. So that's something useful to keep in mind for the remainder of this lecture, and we will come back to that. Now, these last diagrams on the bottom represent the effect of Lorentz transformations on space-time diagrams. So here we have our x versus ct, our standard space-time diagram, and something that we'll call the rest frame. And that's the frame where we consider ourselves to be non-moving. But if we apply these Lorentz transformations to look at the moving frame represented by the primes from the perspective of the rest frame, we actually see that our axes get smushed relative to the light line. The light line is, of course, the v equals c line. And they sort of like shrunk in towards it. And there we get this lovely little angle called alpha, and we can figure out, its tangent and relate that to beta, and then we can, come up with equations relating gamma and beta, and so on. But the main two things that I want you guys to remember from this before jumping forward is that in our space-time diagrams, we can examine other reference frames from the perspective of one reference frame using the aforementioned Lorentz transformation. And of course, remembering that gamma gets bigger as we speed up. Now, let's move on to some new stuff. So the first thing is length contraction. So of course, I've just put our handy little gamma up in the top right, so that way we have it in our mind. And we have two Lorentz transformation equations on the left, namely those for distance in the x direction and time. So let's figure out what happens if we have two distances or two x positions, I should say, in the fixed frame, and these are known. So we have some object with some length L, and let's assume that it's just in one direction for now. It's a very simple one-dimensional line, and its start point is at x1, end point is at x2, and obviously L is just going to be the distance between x2 and x1, which is simply just x2 minus x1. So that's quite simple. Now we can apply the Lorentz transformations to each x1 and x2, and so we get this on the left for the prime frames, or how the prime frame sees the length in the fixed frame, or in the rest frame. So now if we define L naught, or L prime, either way, as the length in moving frame, we will then get that through a bit of mathematical algebra, as you can see on the board, that the length in the moving frame is gamma times L. So the length in the fixed frame, which is L, is thus, if we just divide both sides by gamma and flip it around, is going to be L naught, or the length in the moving frame, divided by gamma. So what does this mean? Essentially, if we are looking at a moving object in another frame, then that object will appear to be length contracted to us. Because remember, as we speed up, the term for gamma gets bigger. And as gamma gets bigger, 1 over gamma will of course get smaller. And that means that as we speed up, the L naught divided by gamma gets smaller, and so length gets smaller, which means that from the fixed frame's perspective, the object in the moving frame is actually going to get length contracted. And now let's discuss time dilation, or rather, the effect of looking at time in the moving frame from the perspective of the fixed frame. And all we're doing here is manipulating the Lorentz transformation equations. So we again have, let's assume that we're only moving in the x/x prime direction, so we just have those two Lorentz transformations, and we are observing some events, or the difference between some events at 2 times, let's say t1 and t2. And we can also find those in the moving frame with times t1 and t2. So if we define, say, capital T as being the difference between the 2 times, or one could call it the delta time, and capital T naught as being the difference between the 2 times in the prime frame, then again, if we do a bit more mathematical algebra, rearrange some terms, as you can see on the left, and if we finally multiply T naught equals gamma over T by T on both sides, and divide by T naught, we get that T equals T naught times gamma. So what does this mean? Well, remember, gamma gets bigger as we speed up. So as our speed increases, gamma times T naught will also get bigger. So this means if, say, 1 second elapses in the moving frame, then gamma seconds will elapse in the fixed frame. And again, since gamma will be bigger than 1, then this is going to speed up incrementally, or rather, our notion of time will speed up in the fixed frame, so time in the fixed frame will go by slower, essentially, and thus time gets dilated. So as we speed up, the fixed frame will make it look like lengths get smaller and times get larger. Okay, so now let's discuss something a little bit different. And this is the concept of a paradox. So as you can see on the board, the definition of a paradox is, quote, a statement or proposition that despite sound or apparently sound reasoning from acceptable premises leads to a conclusion that seems senseless, logically unacceptable, or self-contradictory. So a simple example of a paradox, which you may have heard before, or a paradoxical statement, is that the idea that the only rule is that there are no rules. But you see, that doesn't work, because there's a rule, but the rule is that no rules exist. So how can you have a rule if no rule is supposed to exist? So that's, again, self-contradictory, and is thus a paradoxical statement. Another one, which you may have heard of, are Zeno's paradoxes of motion, which, if you haven't, I highly recommend checking these out. But they were postulated by the ancient Greek philosopher Zeno. And some of them, for example, describe how you can only traverse a distance in half increments. So if you move a distance of 1, you first have to move half the distance, but then you have to move half of that half, and half of that half, and half of the half of the half, and so on, until you essentially, in order to get started, will have to move basically an infinitesimal distance. And you essentially just have to move a distance of 0. But that's impossible, so thus motion can never start. So that's another example of a paradox. Again, if you're interested, I highly recommend checking this out. There are some interesting articles written about this. And lastly, we can also think about paradoxes of motion with regard to special relativity. So let's take a look at one right now. This is a famous paradox, not nearly as famous as the twin paradox, but still a famous one nevertheless, known as the ladder paradox. So let's start by assuming that you have a barn and a ladder. And the ladder is going to be just slightly longer than the length of the barn in the rest frame. So let's assume that the ladder isn't moving for now, and the barn is not moving either, and when you just place them right next to each other, the ladder is longer than the barn. So now let's give the ladder some velocity. We can call it v if we want to, which is the standard notation, and it gives it a speed v in the direction of the barn. So now the barn also has two doors. It has a front door, which we can turn an entrance, and a back door, which will turn an exit. And we can also say that the ladder has a front end, which is the end pointed towards the front door, and a back end, which is, well, the exit that's pointing away from the door. So let's see what happens. From the barn's frame of reference, the ladder, again, because of length contraction, here, let's go back to the formula. So in the barn frame, the barn is going to stay still, and the ladder is moving. Now, the ladder's length is going to be this L0, and the gamma for the ladder is going to be quite large, because it's moving at a relativistic speed. But because gamma is large, then the ladder is going to appear to be shorter in the barn's frame. So since the ladder is shorter in the barn's frame, and the ladder is now just going to be shorter than the barn itself. So if we close the barn doors once the ladder enters the barn, then the ladder should be able to fit inside it. Let's also think about this from the ladder's perspective. So if we go back to our example of length contraction, now the ladder is in the fixed frame, and the barn is what appears to be moving. So for the ladder, the barn's length is going to be length contracted, because the barn is going to be appearing to move with some gamma as well. So the ladder is thus going to be longer than the barn, so the ladder can't fit inside the barn. But if the ladder can't fit inside the barn, then if the barn doors are closed, the ladder is going to snap. So this seems paradoxical, because if you're looking at it from one frame and the ladder is intact, and the other one where the ladder snaps, something seems slightly wrong here. So we want to decide and figure out what actually happens to the ladder. So what I invite you to do is, before moving forward, take a few minutes to think about this on your own. Maybe draw out some diagrams like the above, maybe experiment with plugging in for, say, the Lorentz transformation equations, or looking at spacetime diagrams, whatever would help you best. Sort of visualize the scenario, think about it, and maybe even begin analyzing it. And once you've come up with a solution or a potential guess as to what could happen to the ladder, feel free to move forward. Okay, so I'll assume that you've had some time to think about the paradox itself and come up with a potential answer. So now, let's actually work through this and see what happens. So the first thing we're going to do is just think about the scenario as a whole and look at what's really happening. So in both frames, the barn, which we'll think of as the rest frame, and the ladder, which we'll think of as the moving frame, the front of the ladder obviously has to hit the entrance of the barn, because otherwise the ladder can't get into it. Then the back of the ladder also needs to hit the entrance of the barn, because if the back doesn't hit the entrance, then how will the ladder ever move through it? But lastly, the ladder also needs to move outside of the barn and thus escape the barn. So the ladder must hit the exit door, or here in the diagrams it's noted as the back door. So these three events will always have to happen. A fourth event is that the back of the ladder hits the exit door, but that's not as important for us right now. However, you can feel free to consider that as well. Additionally, there are two main frames of reference we can consider. Of course, there are tons of others, but these two are simplest. So usually when analyzing a relativistic scenario or a paradox, it's always a good idea to look at the frames of reference for the objects in the scenario. Here we just have two objects. We've got the barn, which we'll think of as our rest frame, and the ladder, and we'll think of that as our moving frame. So those are the only two frames of reference we need to think about. But let's start off with looking at the barn and the rest frame, and looking at what these three events match up to. Alright, so the first thing we're going to do is start off with a space-time diagram. So all we need to do are draw an x-axis on the horizontal, a ct-axis on the vertical, and then just draw a line at a nice 45 degrees slanting up and to the right, representing a speed v equals c. So what we're going to do is define the origin, or where x is 0 and ct, or where t equals 0, as where the front of the ladder hits the barn entrance. So when the barn entrance door opens. So the next thing we need to do is figure out when the front of the ladder is going to hit the exit of the barn. And to do that, we need to think about the speed of the object, or of the ladder, rather. So in order to do that, we need to bring in the Lorentz transformations. So if we go back here, remember that when we're looking at, say, the x versus ct axes, the prime frame, or the moving frame, can be represented there by simply smushing the axes, and you can see that more clearly here. You just smush the axes about the line v equals c. So they're both rotated equally about it by this angle here. So, which is also, again, the same angle, alpha. So what we can do now is just represent that rotation. Again, we don't need to note down the angle here, but you can if you'd like to independently. And we now get a ct prime and an x prime axis overlaid upon our x versus ct graphs. So what does this mean? Well, the ct prime axis, represented in the rest frame, essentially shows us how quickly the ladder, in this case, is moving relative to the barn. And you can test this out. If the ct prime axis is extremely vertical, well, then you can tell that as time moves on in the x versus ct rest frame, as time proceeds, then the x variable of the moving frame isn't going to change very much with ct prime axis. So it's moving fairly slowly. As it approaches the light line, however, it begins to speed up due to the same reasoning. And again, feel free to explore this on your own as well. So the first thing that we want to do is also just define where the barn ends. So we'll do that arbitrarily on the x-axis using this little tick mark here in purple, and we'll just say barn end. So the next thing that we're going to do is essentially figure out where our barn ends relative to the ct prime axis. So that is essentially the exact same thing as asking, okay, how quickly on the ct axis will the ladder hit the barn door? And that's just going to basically be right over here at the intersection of, if we drew the ct axis, we drew it, right alongside, going at the barn end and figuring out where it intersects the ct prime axis. And that's going to be right here. So the last thing that we want to do is figure out where does the back of the ladder hit the entrance. So that way we can figure out where the door closes. And if we draw, well, the first thing we need to do, actually, is figure out what the length of the ladder is in this frame, right? Because we don't have a separate event for the back of the ladder at this precise time. Of course, we could very well include one, but that would make this diagram far more cluttered. So instead, what we can do is remember that again, since the ladder is moving, it's going to be length contracted. And since we said that the ladder before was just about, maybe a little bit longer than the length of the barn, its being length contracted means that its length is now shorter than that of the barn. So we can say that the end point, or at the back of the ladder, is going to be somewhere between the origin and the end of the barn. So we're going to draw a line segment parallel to the x-axis because, again, it's moving in the x-axis only, and that's the only axis we're considering here. So we'll draw a line segment from the front hitting the exit, which is right here, to some point, and we'll call that, this right here is going to be essentially the back of the ladder. So now we need to figure out where the back of the ladder hits the entrance as well. So remember, the entrance is always going to be at x equals 0, because that's just how we define the origin. The origin of the rest frame is at the time and position where the front of the ladder hits the entrance, which is, again, just the entrance of the barn at t equals 0. So we need to now move this light line, because, again, all parts of the line segment, all parts of the ladder, are moving at the exact same speed. So we're going to essentially just move this line over just a little bit. It's essentially parallel because, once again, both endpoints have to be moving at the same speed, otherwise something seems off here. And, of course, again, both parts of the ladder need to move at the same rate. And we'll move that over here and look at now where that pink line, the moved CT prime axis, or parallel to the CT prime axis, will intersect with the CT axis, aka where x equals 0. And that occurs right at this purple point here. So we can thus define that our purple point is going to be where the back of the ladder hits the entrance in the rest frame. So now, just by looking at the CT prime, and x axes in the rest frame, we've been able to determine where the front of the ladder hits the entrance, or the front of the ladder hits the exit, and where the back of the ladder hits the entrance in the rest frame. So now we need to mirror this, but we need to do the exact same thing for the moving frame. But let's not switch perspectives. Let's keep being in the x versus CT frame. So what else can we do? How do we get this additional perspective? Well, remember that in both frames, the front hitting the entrance is going to be, again, at the origin of the CT versus x, so that's fine. And the front hitting the exit is, well, that's still going to be along the CT prime axis, because now, again, it's still going to be at x equals 0, or x prime equals 0, rather, because that's what we've defined the front of the ladder to be. But now we've got a little bit of difficulty. So let's go back here and look at our length contraction equation. So, again, now we know that if the ladder is moving, then from the barn's frame of reference, the ladder is going to be shorter. And if the barn is moving from the ladder's perspective, then the ladder is going to think that the barn is shorter, which automatically means that the ladder is going to think that it's longer than the barn. So that means that the distance, essentially, this little blue guy right here, remember we defined that as the length of the ladder in the barn frame. Well, now it's going to look a lot longer along the x prime axis. Now, not the x-axis, because remember, we're looking at the moving frame. So we forget about the x and CT. We're only looking at the moving frame now. And we're going to essentially just draw a line from this blue dot right here, which is where the front hits the exit, parallel to the x prime axis. And that, of course, is going to go here. And this right down there, where it intersects with the CT prime axis, is or the parallel part of the CT prime axis, is going to be where the back of our ladder is. And you can tell that this distance right here is far longer than that of the blue line that we drew before on the x prime axis versus the x-axis. So now we have our complete diagram here, our complete space-time diagram. So we have our three little points for the hitting the entrance, hitting the exit, and then the back hitting the entrance as well. And we now also know our distances of the backs from the fronts in both frames. So with that, we're basically ready for our analysis. So feel free to linger on this part a little bit longer before moving on. I would also highly recommend taking a screenshot so that way we can compare it to our analysis. Alright, so let's go ahead and interpret the space-time diagram. So the first thing we want to discuss is how in the rest frame, or in the barn frame, the sequence of events will look. So let's go back here just into our simple rest frame diagram and start at t equals 0, or even a little bit before. So we just want to move, so we want to essentially draw a series of horizontal lines, if we could, and just move up the CT axis from all the way at the bottom to all the way at the top, and see what events we run into. So the first event that we run into is that the front hits the entrance, which again occurs at x equals 0 and t equals 0. Okay, so the front hits the entrance. Then we keep moving up. The second thing that we encounter is that the back hits the entrance in the rest frame. So the back goes, again, it hits the door. And if we keep moving a little bit further, we'll now find out that the front of the ladder has hit the exit. So let's go ahead and look at this step by step. So the first two things that we notice, as said before, are that the front end hits the entrance, so that means that the barn doors will open, and then the back end hits the entrance, so the entrance door closes. But at this point, the front end hasn't hit the exit yet. So that means that the exit door is still closed. So the ladder is still completely within the barn. And then the front end afterward, as we said, will hit the exit, so the exit door opens. Now, let's discuss what happens in the moving frame. So now we want to look across our CT prime axis. So going from, again, top to bottom, going from here, and now not the CT, but along this pink line, we want to see what events we run into. So, and also remember that the purple point is where the back hits the entrance in the rest frame. That doesn't apply to us here, because we aren't in the rest frame anymore. So let's start by moving up. So the first thing we notice is the front hits the entrance. Okay, now we're going to keep moving, keep moving, keep moving. Again, forget about the purple point. Keep moving, keep moving, keep moving. Oh, look, so the front now hits the exit. And if we keep moving some more, I haven't drawn that in here, but we would eventually see that the back would hit the entrance in the moving frame somewhere after this. So, if we look at our moving frame sequence of events, as we just said, the front end hits the entrance, so the entrance door opens. So the front part goes through the entrance. The front part then goes through the exit too. But remember that the entrance door is still open. So the back door, the back end of the ladder can still go through the entrance, and afterwards the entrance door can close. But that basically means that the ladder just goes straight through. It doesn't ever, when the doors open and close in the ladder or moving frame, the ladder still doesn't get snapped, even though the doors are still opening and closing. So what's happening here? Let's discuss. So in the rest frame, as we just saw, the ladder can be enclosed in the barn for some amount of time. Again, since we're assuming the barn is probably small, it'll be for an extremely small fraction of a second. Likewise, in the moving frame, however, the ladder is too large to be enclosed, and so the ladder just goes straight through without being able to be enclosed. Also, as we saw in both frames, The timing of the opening and closings and their order is different too. So, for example, in the rest frame, the entrance door opens and closes, and then the exit door opens. Whereas in the moving frame, the entrance door opens, then the exit door opens, and then the entrance door closes. So that ordering is different. But one thing to note is that in both frames, the entrance door only closes after the exit door opens, right? So we can see that right here, for example, and up here as well. And thus, the ladder doesn't snap. So essentially, the ladder can go through, and in both cases, without being snapped apart. So what's going to happen? The ladder is fine. Now, what does this mean about the problem? Does it mean that the problem's premises are wrong? No. Well, it also just shows that we needed to do a more nuanced analysis compared to the premises that we are given. Alright, so now let's discuss the lessons from the ladder paradox that we can learn. The first thing to note is that the relativity of simultaneity is really important. Events are not simultaneous in all frames, and are not going to be simultaneous in frames that move at different speeds. This was something that we covered in part 1 as one of the foundational lessons that came about as a result of the speed of light being a universal constant. And we can see why it's so important here, because that defines why we only get one result, one physical event in all frames. So, as the next point says, this also means that physical events are the same in all frames, but the time and positions at which they occur may not be exactly the same. However, and we can see why this could happen, right? So let's say, for example, that in one frame, say, a person is dead, whereas in the other one, a person's alive. Which is, again, what would happen in a sort of paradoxical scenario. So that essentially means that two frames would mean two realities in the same universe, which is clearly impossible. So in both frames, the person must either be alive, or in both frames, they must be dead. It's impossible for it to be different in each. And we can see that with the ladder, too. So in both frames, the ladder must either be snapped or be unsnapped. It can't be snapped in one and unsnapped in the other. So thus, here, the ladder is unsnapped in both frames. So one last thing to note is that Lorentz transformations could have gotten us to the same conclusion if we had, for example, if we wanted to examine how quickly each point, was reached for, say, the front end hitting the entrance versus the exit versus the back end hitting the entrance and exit, and we could examine that in both frames and compare the change in times and see which ones happened earlier, and so on. It's however, as we saw, far simpler to just draw a rough diagram using spacetime diagrams, or an accurate diagram using spacetime diagrams if you wanted to use precise numbers. But either way, we can get to a conclusion far faster, which is why I highly recommend using spacetime diagrams to analyze these sorts of basics paradoxes. Alright, so that is the conclusion to our main part of the special relativity 3-part series. So, what have we learned so far? Well, one thing to note is that the world looks different from different reference frames. And that is something that we discussed far earlier. For example, if you're in a car and you're tossing a ball up and down, the ball just looks like it's moving straight up and down. But if you're standing outside the car, the ball looks like it's moving in a parabola. So again, even without relativity, the world looks different from different points of view, different reference frames. Next, physical laws and the speed of light must be constant between all reference frames. This is something that Galileo and then Einstein, with the speed of light part, postulated, and this is the basis of our theory of special relativity. Additionally, we learned that the space-time interval between two events must be the same in all frames, and events are not simultaneous in all frames. So using these very simple rules, we're able to derive more complicated things using this relativistic toolkit map. So the top diagram with the moving flashlight and boy demonstrates to us that, again, the speed of light is a constant, regardless of if you're moving, if your flashlight's moving, the speed at which the light hits your eyes is still going to be the same, roughly 3 times 10 to the 8 meters per second. We can use that to derive our equation, combined with the Pythagorean theorem and some modifications of it, to derive the equation for space-time intervals and determine their invariance in both frames. Then, using the invariance of the space-time interval, along with, of course, its formula, we can use that to determine the Lorentz transformation equations, which are in the bottom, assuming motion only in the x direction. Now, if we had motion in the y and z directions, the Lorentz transformation equation becomes slightly more complicated, but not very much so. We can also use space-time intervals and its invariance to create space-time diagrams, which on the right is a two-dimensional x versus t one, and invariance of the space-time interval creates those curves of invariance, those invariant hyperbolas that we can see as on the left, up, down, and right triangles of that diagram. Those also demonstrate to us why exactly we have the cosmic speed limit as v equals c. Additionally, we also discovered that through the Lorentz transformation equations, it's really easy to just take out a factor of 1 over the square root of 1 minus v squared over c squared, which is basically gamma. And using gamma, we can also derive the equations for length contraction and time dilation, which are listed on the right. So, using all of this stuff, what can we do? Well, as we just discussed, we can explore paradoxes, weird scenarios that may or may not have a clear resolution, and use them to figure out, well, what actually happens. In addition to the ladder paradox, there are many more paradoxes to explore, which I highly invite you to do as well. There are things like, for example, Bell's spaceship paradox. What happens if you have two accelerating spacecraft attached with a rope, and they move at relativistic speeds? Will the rope snap, or will it stay together? You've got things like the twins paradox, and faster than light, the impossibility of faster than light communication. Sublease paradox, where a relativistic submarine sink or float, and even more. So again, I highly recommend you to check those out and utilize space-time diagrams in combination with Lorentz transformations, if you're interested, in order to approach precise solutions. There are also more mathematical and more nuanced things that you can explore. For example, there is a concept called form momentum, which is essentially momentum in x, y, and z, but also, weirdly enough, in the t frame. So how does that work? And why is form momentum preserved in relativistic collisions? There are also examinations of accelerating reference frames, where the Lorentz transformation equations themselves don't currently work because we don't just have a velocity, we also have a non-zero acceleration. So how do we figure out what happens in those sorts of instances? You can also use form momentum to derive the equation of E equals mc squared and look at its consequences. Additionally, there are also lots of practical applications to special relativity. Instead of these sort of outlandish scenarios of ladders moving through barns at relativistic speeds, we can look at things like quantum mechanics. We can look at stuff like the black hole information paradox, of how can information be transmitted through a black hole, how is information preserved within it. And we can also look at particle physics. So one of the most useful applications of form momentum, relativistic collisions, along with the Lorentz transformation we just discussed, is actually CERN and the Large Hadron Collider, which regularly analyzes particle tracks. And if you examine form momentum and relativistic collisions, you can use them to analyze particle tracks of collisions of, say, two protons or two hadrons or whatnot together, and look at what is produced outside of them. And that's actually how the Higgs boson was originally discovered. So there are tons of fascinating applications to special relativity, which I hope that you will be interested in checking out after this lecture. Alright, so that concludes our 3-part adventure into the realm of special relativity. Next time, we'll discuss general relativity, which is slightly more complicated than special and considers the effect of mass on spacetime. Thank you guys so much for coming, and we will see you next video.